Okay, ladies and gentlemen, and for the final lecture on Track A in PHP Conference Serbia 2018, Michael Cullum. In his talk, he will speak about how you can, in your PHP applications, perform utilise machine learning techniques to build models, analyze data to get useful information, and spot anomalies. Michael, fire at will. Thank you.
So it's the end of the second day. It's the last talk. Who's had a great conference? So my mission, because you've had a lot of information over the past 2 days, I imagine, and you've all learnt a lot, right? So this is going to be quite information heavy, but I'm going to try and make it exciting. I'm going to try and keep you all awake, and then we'll get through and then go to a social afterwards. So let's get started. Very quickly, who am I? My name is Michael Cullum, and that's my Twitter handle. If any of you want to tweet at me throughout the talk with feedback, comments, or even abuse, I'm up here for the next hour or so I can't defend myself. So go for it. I work for a company called Sam Knows. We do internet performance measurement data. Which sounds really boring, but it's actually really cool. We do big data and machine learning and all sorts of other buzzwords. I'm also the Symfony security lead. Who uses Symfony? Quite a few of you, fantastic. It's my job to make sure that the libraries that you're all using are secure. No pressure. I also, I used to be a secretary of an organization called the PHP Fig, which is a standards group for PHP. And I'm now on the core committee for that, so I'm now kind of like one of a bunch of people who steer the direction of that. If you want to talk to me about those, then come chat to me afterwards. And finally, PHPBB. Who's used PHPBB? Who has used it in the past year? Fair enough. We still have 25 million installations, so still a fair number. So I'm also on the management team for that. It's a lot more secure than it used to be. But you're here to talk about artificial intelligence, right? Machine learning, all of that fun. Artificial intelligence, it's complete rubbish. Realistically, until you present me with a robot who can have a conversation with me, can understand what I'm saying, can learn from me on a continual basis, I say artificial intelligence doesn't exist. Maybe it will one day, and then we're all kind of stuffed. But it doesn't exist right now. What does exist is machine learning. Machine learning is actually just basically a buzzwordy way of saying statistics. That's what we used to call it, but now we call it machine learning. So let's dive into that a little bit. What is machine learning? To put it simply, it's machines that do learning. But what is learning? It's something we've all done, but it's actually quite an odd concept to kind of think about. The learning process. So we initially take a cause and effect. We see a bunch of things happen in our lifetime. We use our eyes, we hear things. We process what we see or what we hear. We add context to it. And then we store that into our knowledge base, into our database in our head. And that's basically learning. When I see something happen, so if I drop my clicker, and hopefully it will still work afterwards, then I'm observing that it falls to the floor. That's a cause and effect. I drop my clicker, it falls to the floor. I have seen that happen, so I store that in my head, and I add that to my knowledge. And therefore, I kind of know how gravity works. And then, when the next time I go to do something, I predict the outcome. So if I take this water bottle and I drop it, I'm predicting that if I release it, then it will drop to the floor. And it does so. I'm just trashing this stage. So in that situation, what you're actually just doing is prediction. So machine learning is all about seeing cause and effect, and then eventually taking a prediction from what we've kind of stored in our head. We've built a model. Now, when we look at numbers, it's exactly the same. If I give you 1 plus 1, that's a cause, and the effect is 2. 1 plus 2 equals 3. 3 is the effect, 1 plus 2 is the cause. Now, you don't need to know maths in order to see that. So I've got a whole bunch of stuff up there. So I've stored that into my knowledge base. I've learned that. I learned that when I was a kid. It's become my knowledge. So then, when someone says, what is 3 plus 1, I don't actually need to know how to do maths, because I can predict what the outcome is going to be. I predict it's going to be 4 because it's over here, because I've already been told what it essentially equals. And that kind of comes back to fundamentals of programming. You tell it to do something, and then it does a repeatable task. We can also be a bit more clever, though. Most people in this room can do simple maths, I hope, right? Yeah. Now, if I told you 256 plus 3, you were never told as a kid that 256 plus 3 equals 259. You just have developed a skill of how you can change what you know to fit the context. So if I gave you these, 1x plus 3 equals 4, and 1x plus 4 equals 6, 1x plus 3 equals 5, 2 plus 3x equals 8, I can begin to infer that what I'm actually doing, if I already know about the skill of multiplication, is that whichever number has x next to it is doing a multiplication, and it's doing it by a number. So if I then added the context of, in the first instance, x equals 1, x equals 2, x equals 2, x equals 2, they're all 2, then I could then go and complete a new equation that I'd never seen before. If you told me that x equals 10, I said 1x plus 4, then I know the answer is 14. Simples, right? That's learning. That's applying what we've learned in a situation we've never seen before. So why can't a machine do this? And it's very similar the way that we learn normal human concepts. So, for example, when we're learning languages, I only speak English because I'm frankly less competent than the rest of you that can speak more than one language. And therefore, I see this thing, these objects quite regularly when you're a child, and I hear the sound eggs associated with it. And I see people eating it. I see people putting it in their mouths, so I assume that it's a food. That's generally what goes into people's mouths. And then I see these letters associated with it, E-G-G-S, eggs. And that's how I've learned how to spell, what the word is. That's how we learn languages when we're children, particularly your first language. And a lot of language teaching is centered around this whole idea of, don't just sort of sit them down with a dictionary, but get them to try and work it out for themselves in the same way that you do your first language. I failed though, so maybe don't listen to me about language. So, machine learning. Let's apply this to machines, right? It's a 4-step process. First of all, you have to acquire your data. Secondly, you train a model. So that's sort of your learning. Then you ask it a question, and you get an answer. Sounds simple, right? Let's dive into each one of those stages in a bit more depth. So firstly, acquiring data. This is probably actually the hardest step. If you're a long-established company, you might have quite a lot of data, whether that be log data or another kind of data. I can't really give you many tips on how to acquire data, so good luck. Come up with a great idea on how to collect some data that will fit your model. Ideally, you want sort of good, clean data. You don't want sort of erroneous data in there. But erroneous data exists, right? That's a fact of life. Secondly, you train your model. Sorry. Now, there are two different. This is the machine learning part of machine learning, right? So we have two different kinds. We have supervised learning and unsupervised learning. Just the same as at school when you went and learned English by yourselves, and then when you were at school, you were probably taught maths. There's supervised and unsupervised learning. So let's dive into what those two actually mean. So we've got supervised learning. So with supervised learning, that's where you have known outcomes. And that's where I can say that I want to classify something, for example, into a bunch of different groups, and I know what those groups are. And I have some examples that I know also fit into those groups. And there are two different kinds. There are lots of sort of different derivations here. We have quantitative and qualitative. And I'm kind of going to focus on a few areas of machine learning and trend analysis in this talk, just kind of to simplify things. There are others as well. So we'll talk about classification and regression. So first of all, we'll talk about classification. So what I've done here is I've rated something. It doesn't really matter what I've rated. And I've got a series of my different ratings that I've given it. I've got 100, 25, 50, 40. It might be a test. It might be I'm rating beer. It could be anything. And then I've said whether or not I consider that rating to be a good rating or a bad rating, a very binary choice. I've got my two different groups, my two different classifiers there, good and bad, simples. Now, I've drawn a graph on the right-hand side. In this particular instance, it's a bit more obvious without a graph, but particularly as you sort of get into more complex trend analysis, machine learning, that kind of thing, graphs can really help you kind of visualize the data and see the patterns, and you can sort of see if your model actually applies. Graphs are amazing. I cannot cannot express how useful they can be in trying to visualize data as humans, particularly when you just see a whole load of numbers on the screen. So I've just put those points on a graph. If I add some more onto it, I can kind of draw a line, and I can say where I think above this is good, and and below this is bad. In this case, I've just put it at 50. So 49 or below, that's a bad rating, and above that is a good rating. That sounds really simple, right? But we've actually done something quite intelligent there. We've been given some inputs, and we've predicted the answer. We weren't told what the answer was. We weren't told that if I plugged in 49 into this algorithm, then it would be a bad rating. It's not, as I said, artificial intelligence is rubbish. It's not intelligent, it's just making a guess, in the same way that we as humans would. Now, it can get a bit more complicated. So in this graph, for example, it's a series of plotted points. And what we've done is we've given a group of people two tests. We've given them a test on sales techniques and PHP. Now, we know that the two different types of people that took this test were PHP developers and salespeople. Now, as you might imagine, salespeople were good at the sales test and really quite bad at the PHP test, and vice versa. People who were good at the PHP test were bad at the sales test. So we've kind of got these two distinct groups here in the bottom right-hand corner with the sort of white dots. We've got the people who did well at the sales test, and top left we've got the people who did well at the PHP test, PHP developers and salespeople. Now, we want to try and find a way where if we plug in two scores of a sales test and a PHP test, is this person most likely to be a PHP developer or a salesperson? So I've drawn some lines, because lines are cool, right? The green line on the right-hand side, if we look at that, it kind of appears right in a certain way, because on one side of it, we have only salespeople, and on the other side of it, it's a bit more mixed. But we have that right side, which is actually completely correct. So if it said if it's on the right, then it's a salesperson, it's a good algorithm. But we can do better, right? So we've got the blue line going straight down the middle. Now, this actually divides it perfectly. We can see that every single salesperson is on the right-hand side of that line, and every single PHP developer is on the left-hand side of that line. So it's perfectly classified our groups. However, it doesn't feel right. And this is where actually putting something into a graph can kind of help you understand your data better. Because this red line sort of going across diagonally, that feels like a much better fit. You've got all the PHP developers in one corner, and you've got all the salespeople in another corner, and the points are roughly the same distance away from the line. They're not sort of like in varying distances. So I'll talk about algorithms and how we can actually do this kind of stuff in a bit. So the other side of this, of supervised learning, is regression. So regression is all about being given numbers and being able to do things with it. So in this case, I'm looking at the price of paintings. So we've got a bunch of different prices. We've got 5, 6, 4, 3, whatever currency you happen to be talking in. And then we've got the sizes. We'll say they're centimeters. So for a 10 centimeter painting, I'm going to be paying 6. But for a 5 centimeter painting, I'm going to be paying 3. Now, I've kind of simplified the numbers just to make the graph look a bit nicer. But we can see that there's a nice trend there, right? That's just done completely visually. I can see the larger the painting, the more expensive it is. Makes sense. Now, if I said that I wanted to know how much a £1.50 painting should be worth, I can use this line that we've kind of derived, this line which we've made up for our prediction of future values. And I can say it would probably be, if it was 2.5 centimeters, I can say it would be roughly 1.5, just simply by adding an extra point on the line and seeing where it matches up. In the same way, I could do it in the other direction. So that's regression. Simple, right? So unsupervised learning. Now, unsupervised learning is all about when you want a machine to discover something new. It's when you want it to tell you something that you don't already know. You don't know the different groups of people. You don't know the different types of customer. You don't know the different types of error, whatever you happen to be sort of analyzing. Now, again, this can kind of fit into two categories, which I'm going to talk about. One is association, and one is clustering. So association. I think the biggest supermarket here in Lithuania is Maxi. Is that fair to say? OK, great. My local knowledge is a bit lacking. So say we work for Maxi, and we're looking at all the purchases in the past week where people have purchased 2 items. And we put them together in a table in the order. And we want to draw some assumptions from this. We want to discover some things. And so we do. We say that people who buy socks also often buy underwear. And that's what our data tells us, right? Because we can see that generally when people are buying socks, almost every time they've also bought underwear at the same time. So we can make an association between those 2 products. Now, the other thing that we can derive is that people who buy underwear always buy socks, because every single person in our sample who has bought underwear has also bought socks. Now, I don't know about you, but I've been out and I've bought just underwear before, and I've been out and just bought socks before. It's not fair to say that every single person who buys underwear also buys socks. But as far as our sample is concerned, that's what the data is telling us. And this kind of highlights the first flaw in unsupervised learning. It can make assumptions based on the data that you give it, but sometimes it just doesn't simply know enough. We as humans, we think we know lots about black holes and general relativity and all of that kind of stuff. But then we discover something brand new, like Higgs boson or something like that. And then we're like, actually, we didn't really understand the full scale of things. The predictions we made were wrong. And then what we can do is adjust our models. And that's because we, as humans, are doing unsupervised learning on a daily basis. That's what research and development is. It's all unsupervised learning, but with humans. And this is just applying it to a machine. A machine can be wrong, but so can we. We just happen to have more experience than this particular model. I can make some other assumptions here. People who buy suits always buy black shoes. People who buy black shoes also always buy suits. Again, we can see these assumptions are wrong, but that's just, again, because we have more data than they do. And similar for T-shirts and shorts. So, clustering, the other side of unsupervised learning. Now, clustering is actually a really hard thing to define. And when I was prepping this talk, I was looking around, and I kind of had a look at some dictionary definitions. And what a dictionary definition of this is, and this is complete rubbish. It's not helpful at all. Cluster analysis is a task of grouping a set of objects in such a way that objects in the same group are more similar to each other than those in other groups. And I'm like, that doesn't help me at all. I'm trying to explain this in a way that makes sense and is easy to understand. And then I kind of thought about this phrase a bit more. And if you pick out certain bits of it, it can make a bit more sense, and it can be a bit simpler. So essentially what we're doing is we're doing grouping of some kind. We're grouping a set of objects. And what we're doing is when we find these groups, we're putting them in a group where they're more similar to everyone else in the group. Now, that can be quite complex, because we can be wrong. We're talking about where they're more similar. We don't actually know that that they fit into that group. Take nationalities, for example. You might take 2 people, you might take a Brit and American, and have these as kind of 2 groups where they're quite similar. But then you might take someone who's German, for example, and say, okay, they're a different group. But what happens if they have dual nationality? Or what happens if their passport is German, but they were brought up in Britain? They might be more similar to a British person, but we've put them in the wrong group there. So again, we can kind of see the flaws with unsupervised learning from this, in that we can try and guess what they're more similar to, but that doesn't mean that's what they actually are. More graphs. So on the left-hand side, we can see a very simple kind of set of cluster distinguishing bits here, because we can divide it with straight lines. If you can do stuff with straight lines, it makes your life so much easier when you're doing statistics, trend analysis, machine learning. But sometimes it's not that simple. The graph we have on the right-hand side, it curves around. I think we can quite clearly tell that all the red dots are kind of associated with each other. They're all part of that one blob, but it's curved around the blue blob. So we have to be a bit more clever than we were previously with sort of straight lines and be able to handle that kind of case. And then we get on to step 3 and 4. We ask it a question. We say, as I sort of demonstrated earlier, how much would it cost if my painting was going to be 1.5 centimeters, and it gives me a price. That's the predicted answer. It might not be right, but it's its prediction. It's as good as it can do. So, the actual algorithms sort of behind all of this and how we can do this ourselves. First of all, I'm going to talk about something called least squares. Now, when you're at school or college or whatever, you probably did a scatter plot, lots of sort of points on a graph, and you draw a line of best fit, and you would do it with your eyes and kind of with a ruler and sort of go, I think it kind of goes like that, maybe-ish. That's terribly unscientific. And a machine can't do that. It can't guess. It can't think, oh, that's what kind of looks right. It needs a formula to derive that. And that's what this line here is. So this is a perfect line of best fit in this instance. You can have other lines of best fit where they're sort of curved, but I'm not going to go into that. So I'm going to jump into a bit of maths, because we all love maths, right? So obviously we have people with a huge different range of backgrounds in here. The equation of a line. Who knows about the equation of a line? Just kind of give me an idea. Okay, most of you, fantastic. A plus bx equals y. So a and b, those would be numbers. So you might have 3 plus 4x equals y, and that's an equation of a line. And the idea is that you can put in any number into x or any number into y, and it would give you the other value, so you can then draw that straight line. Now, that's what we're trying to achieve here. We've got our sort of line back there. We need to know what this line looks like, and the way that we convey it is with this equation. So, least squares regression line. The process is every point has an x and y value. We need an equation. So what we kind of want to do is we move this line, and we put it in an infinite number of places in the graph. And every single time we've drawn a line, we draw a square between it and that line, with one corner on the line and the other corner on a point. And we draw lots and lots of these boxes until every point on the graph is joined up to this line. And the correct line is where the sum of all of those squares is the smallest. Now, that sounds kind of complex to kind of visualize. So I've kind of got a little demo, which I'll just show you. Cool. So, hopefully. Okay, one sec. I have an idea. Okay. Right, let's try this. Right, so I can't actually see this on my laptop screen, so I'm going to have to kind of do it on the projector. So here what we're seeing essentially is the equation of a line. And these two things here, I can click and I can move the line. So the first value, I didn't actually explain what those values are. The first value, this one here, is where it intersects with the axis that we see on the left-hand side that goes up. So if I sort of adjust that there, you can see the line goes up and it goes down. So I'll put it back. And the second line is basically how steep it is. It's called the gradient. So I can just kind of move that around and sort of we're just changing the angle of that line. Now, we can see sort of this point here, for example, and we can see the point at the other corner of the square that's attached to the line. And what this demo on the right-hand side is showing us is it's showing us the sum of all the squares. So if I sort of move this here, we can see the squares get really, really huge. If I do it like that, they're also really, really huge. I'm not even sure where the line is at that point. And again, I can sort of move it on here. It will change the size of the boxes. Now, the perfect line here, right, it's actually 0 plus 1, I think. So if I very carefully do that, this is very hard on the projector. So that's as close with sort of just with going around those sliders as I can get to a perfect line. So all the sum of all the areas of all the squares is the smallest that it can be. Now, that's kind of inefficient, and that's kind of inefficient. And when we want to do it in PHP or any other language, we need to come up with like a mathematical way of doing that. So first of all, I'm just going to show you how we can generate that line in PHP. Oh, this is going to be fun. Cool. Let's bring that across. Awesome. So, that one up there. I'll make that bigger. There we go. So what I'm doing here is I'm giving it a training set. I'm building my model sort of up here. I'm giving it a series of different values. I'm giving it my x values and my y values. It is possible to have more than one dimension. So you could have x, y, and z. You could have as many dimensions as you want. But I'm not going to go into that today because it's complicated. So essentially what I do is I build my model. I say that least squares. So step one here, acquire data. Step two, I'm training my model. I'm giving it the inputs, and I'm giving it the outputs, the cause and the effect that we were talking about earlier. And then I say, predict what the value is going to be when it's 60. So I can just do that. And it gives me a value down here, which you can't really see. There you go. So it's saying that if I have 60, then it's roughly 3.3. Now, that doesn't kind of seem right, because I'm actually telling it what 60 is. I'm telling it that 60 is actually 3.1. So why is it telling me 3.3? That's a different number. And it knows what the real answer is. Now, if we think back to that graph we were looking at earlier, the line didn't go through every single point. However, what we're actually getting back out of it is the value on that line. It's not going to be perfect for every single number. It'll be perfect probably for about one. But it might not be perfect for any of them. It's going to be as close as it possibly can be for all of the different situations. So if I go and do 64, and I run that, then we can see it's predicting in the other direction. So 64, it's slightly under what it should be. We would have guessed that it would probably be about 4.5, but it's saying just 4. 4.05, sorry. But it's saying 4. So it's going under, whereas another number we had, it was slightly over. So it's never going to be exactly accurate. But it's still close enough, right? It's giving us an idea. So the library that I was using there is called PHPML. It's a nice, tidy little library. It's not perfect, but it's nice if you kind of just want to have a play with some of these models. It's got a whole load more that I haven't talked about in this talk as well. So it's worth having a play. My slides were tweeted out when I started my talk, automation. So if you want to sort of have a look at that, my slides are up on my Twitter, so you can have a look at find them there. So that's the code. In terms of the maths of how that works, I was asked this last time I did this talk. it's kind of complex, so I kind of don't want to go into too much detail, but in case any of you are curious and know how matrices work, you basically take matrices of the targets and of the results. You do some transposing, you multiply them by themselves, you then inverse the matrix, multiply the target matrix that you've kind of done all of that manipulation on by the samples matrix, and then multiply all of that by the samples matrix, and then you multiply those two together, and then you get your coefficients. Now, I appreciate that's quite complicated, but if you want to have a look into that, then feel free to have a look at the slides afterwards. The point I'm making is that when you do it in a programming way, we're not moving that line and putting it in an infinite number of places. There is a mathematical way where we can kind of work out where it should sit. Nearest neighbor, the next algorithm I'm going to talk about. So we can see a huge number of points here, and they've already been classified for us into green, blue, and red. Now, if I was going to use nearest neighbor to sort of do this clustering for me, then it might look a bit like this. Now, if I then added an extra point, say here, then I would assume it to be blue. If I added a point here, then I would assume it to be red, despite the fact there is actually a green point over there. It's never going to be 100% precise. Now, the way that nearest neighbor works, it's also called like k-means. Now, we're going to experiment with something called 3 nearest neighbor. And essentially what it does is it's really simple. I specify a point, and I look at the nearest 3 points, and I say, what are the majority of them? In this case, I'm the green dot, and I look to my nearest 3 people, and I say, hey, what are you guys? 2 of them say that they're red triangles, and 1 guy says that he's a blue square. So I say, the chances are I'm probably a red triangle. So I'll be a red triangle. But we can also change this really simply by changing k. So this is a 3 nearest neighbor, so I'm looking at the nearest 3. But say I want to look at the nearest 5. And if I look at the next 2 that are nearest, and they're both blue squares. So simply by changing the algorithm, I've actually re-identified myself as a blue square. Now, is that more precise? Is it less precise? Don't really know. And the thing is that it really depends on the data set that you have as to whether a higher k or a lower k is more appropriate. Although generally it's known that stick with odd numbers as convention. So again, I have a little demo of that, which I'm going to have to do this fun for again. There we go. So we're doing our step number 1. We're acquiring our data. Now I'm saying 0.13 is A. I am saying that 0.14 is A, 0.24 is A. So those are all the ones that are actually in the top right-hand corner of a graph, if you're imagining it with you. And then we've got a series of other points, 3 other points that are classified as B. So if you're looking at a graph, that's down here, and A is up here. Now, then I build my model, I train my model, I learn, and then I ask it a question. I say 1, 5. What is that? Is it that A or is that B? And if I run this, then it will tell me it's A, which sounds right, because 1, 5, that would put it in the top left-hand corner of the graph. But I could also try 3, 2. Not 13. I have no idea what that would result in. And it tells me B, which again seems correct. That'll be in the bottom right-hand side. Now, essentially, that's the way that this builds a model. Is it will build a model of the area in which the areas in which A belongs A has, and the models in which the areas in which B has. So visualizing that as a graph, because I was trying to do that with words, but it's always clearer to see it. This is what our training data look like. So we can see the data here in the top left, which is A, and we can see the data in the bottom right, which is blue, which is B, sorry. That's quite confusing, actually. Oh, no, B is blue, that's fine. We add on our 2 new points, which are the 2 that I just tried. And we can see one of them is quite clearly blue, B, and one of them is quite clearly red. So we can see that our model actually in that instance seemed really accurate. Yay, we actually had one that worked, unlike the linear regression, which we can see had flaws. I've just got some code in the slides as well if you want to have a look at that afterwards. So, uses of machine learning. This all sounds great, but like, what can you actually use it for on a day-to-day basis? Numerical analysis. It sounds kind of boring. It sounds quite out there, but there are a whole bunch of ways that just analyzing numbers is actually really useful and can add value to your business. Exceptions. Who logs all of their exceptions in some way? Sentry or the like? Yay, most of you. The rest of you that aren't, please do. It'll be great. You'll love yourselves. Exceptions. You can monitor to sort of say, if I suddenly see a spike, then let me know. I can anticipate sort of, you might get more exceptions at certain times of day. Why is that? You might be looking at certain types of exception, like validation errors, and use that to sort of trace down errors in usability, for example. E-commerce. Earlier, I was talking quite a lot about sort of Maxi, but for them, it's a big business to sort of know what their customers are most likely to buy. Who uses Amazon? Basically everyone. Who has ever bought something that Amazon suggested to you that you should buy and you hadn't thought of buying before? When it said, oh, you might like to buy this. Quite a few of you. They must make huge amounts of money out of that. You didn't go on there to buy it, but you thought, oh, actually, I'll have one of them. And then you bought it. So sort of identifying trends with customers and what they're most likely to buy can immediately add huge value to your business. Fault detection, I kind of talked about this with exceptions, but you can use it for servers. You could use it for sort of network issues, usability even. Root cause analysis. So Sam knows where I work. We build an analytics engine. So we actually want it to kind of tell us, if this happens and this happens, try and find out what caused that to happen. But you can also do that sort of with exception handling, for example, as well. And then finally, classification. Say that, for example, you run a news site or a blog, for example. You might want to sort of say, oh, well, if I want to automatically tag all of my articles to make sort of SEO or something like that. Now, machine learning can do that for you. A friend of mine built an algorithm that could sort of predict newspaper headlines based on sort of natural language processing. All of that is kind of classification. I mentioned natural language processing. Analysis of support queries. You might want to see, oh, we've had an uptick in support queries that relate to a specific part of our functionality. Maybe we need to make it easier to use. We've on a Friday night at Deliveroo, if you work at Deliveroo, for example, you might see that more people complain about their food being cold than on a Saturday night. And you could sort of investigate why that is. You could see, when you've done a big deploy, you could see, is there an uptick in support tickets going on? It's not a substitution for communicating with your team, within your company, but it's certainly a good way to sort of aggregate a huge amount of data at once, particularly if you have a large support team. Analysis of a large number of documents. A friend of mine works for a law firm, and I don't know if any of you have much experience with like a legal process. But there's a stage called discovery, which is basically where you give the other side, in the beginning of a sort of legislation process, an arbitration process, and you give them as much documentation as you possibly can. The reason you do that is that there might be something in there that will compromise you. There might be something that they can use against you, and you have to give it to them. And the way you hide it is by giving them loads and loads of documents, so that it costs them lots and lots of time and money to find that one little nugget. Now, what they do at this law firm is they use machine learning, so as soon as they get all that data, they use machine learning to analyze all of those documents and say, is there anything we think might be useful in that huge trove of documents? So instead of having to pay 100 people to work for 3 weeks analyzing all of those documents, they can just sort of say, run it through an algorithm, and it says, oh, by the way, on that day there was an email which you should know about. And then finally, it's fun. it's really nice to sort of just go and have a play with, sort of see what it can come out with. Now, it's the only way kind of to deal with this is with machine learning is sort of just like diving in and having a play with it. And it is really fun, the sort of kind of stuff you can get out of it. So I would suggest just going and having a play. Thank you very much.
Any questions for Michael Cullum? Okay, we have one. Just a second, we're going to give you the mic.
Hi, you showed us that PHPML was the greatest product ever. Is it any drawbacks using this library?
Yes, so we don't actually use PHPML. Sam knows where I work when we do some of this stuff in PHP. The reason for that being it can struggle with a large amount of data. The best way to kind of build a really useful model is to throw a whole load of data into it. PHPML, the way that it's kind of built around memory, it doesn't really handle that very well. It also has issues with number precision. So I don't know how many of you have kind of dug into like floating point fun in PHP. But basically, you can do things like 0.7 plus 0.3, round it, and you'll get like 1.2. So, it doesn't handle that at all, which means that you can get some inaccuracies, which might not matter on a small scale, but they matter on a big scale. That said, it's a great project to go and have a play with, just sort of to get an idea about how the concepts work. So yeah, would still recommend it.
Thank you. Good. Any more questions? Oh, we have it here.
Okay, we have many libraries for machine learning in Python, PyTorch, Pandas, and so on. PHP should be slower than Python, and how it's slower than Python? Do we have some workbench tests and so on?
Yeah, so I'm not going to say, if you argue that PHP is a language that can be used for every single use case, then you're blinded by how awesome PHP is. It's not always perfect. It's not a one-size-fits-all. Python is significantly better at machine learning models and statistics. That said, if you have, say, a PHP API, and you want to be able to do a little bit of analysis in that, then using a library like PHPML might help you out there. If you're a PHP shop, all of your developers are PHP developers, and building something in PHP, it might not be as efficient, but it might still, but the value trade-off of hiring a Python developer or training at least one of your team, because you can't just have one person who knows how this part of the system works. You'd have to train multiple people in Python. So sometimes it makes more sense actually to just deal with that performance trade-off and do it in PHP. Any more questions?
Going
Awesome.
once, going twice. Sold. Okay. Thank you, Michael. Okay, we're going to pick you up later. You remember all those activations I was teasing you to go up there and take part? Just before our closing ceremony, I have the honor to invite Dr. Eric Everard from Platform SH to the stage. Please welcome him with a big applause. Welcome. And you have Kim Jong-un starter pack. So the winner of Platform.sh contest is Dusan Lukic, who made paper airplane. Congratulations. Okay. Oh.
Čestitam.
Okay.
So you had absolutely a marvelous design. So now you can deploy to the moon, and you can also deploy on Friday, like all of you can after having known us. Well, it was a wonderful conference. Thank you.
Oh, thank you very much. I would just use this opportunity to ask Dusan, how did you manage to keep it up so long?
Good design and a strong hand.
Okay, congratulations once again.
Thank you.
Okay. Okay, guys. Okay, before we see our president here back again, not that president, but the other one, PHP Serbia president, I would like to thank to all of our sponsors. So I will, try to be as fast as I can. You just give a big applause at the end. Thank you, Performance Technologies, ESAM, FactCool, Blackfire, Platform, Catena Media, Hello World, Mainstream, mCloud, SiteGround, Content Insights, Navis, Platform, Deploy, Guarana, Nescafe, Tricoder, GitHub, JetBrains, TMS, and everybody else. Okay, and now the big applause for Aco Gagic, PHP Serbia president.
So, the last talk. Ladies and gentlemen, speakers, colleagues, and my dear friends, I want to thank you all for taking part in our 6th PHP Serbia conference. According to your feedback, we succeeded in raising the bar even higher this year. In these 3 days, we had amazing workshops, great lectures, and lots of fun. I hope you all enjoyed it as much as we did. Hopefully, we will see you all next year here, and we will try our best and invest even more time and effort to organize another conference for you. We couldn't have done it without you. And let me just once again say thank you. And let me rephrase that. And let me just once again say a big, big thank you all. And now I would like to call my team members that managed to organize this conference for you. Please welcome Nikola, Milan, Nemanja, and Nikola on stage. Our amazing staff that was involved in all activities in these 3 days. Please welcome. And now PHP Serbia members are a supporter of this conference. Please. And I would like to call our speakers on the stage once more. Please, a round of applause for them. And thank you all.
So this is the time for a big photo. Do we have that kind of a lens? Where's the drone?
Where's the drone? Thank you all once again. See you next year.
Beer time, middleware track.
Beer time, middle track.
Enjoy the party. Thank you. Super.